Hi everyone. In this video we're going to pick up where we left off on February 6th and continue our discussion of Section 2.4 on the monotone convergence theorem. So remember that a sequence AN converges to a limit A if given epsilon bigger than 0, there's an n, a natural number n, such that the distance between an and the proposed limit a is less than epsilon. Whenever little n is bigger than or equal to this special threshold, capital N. Okay, so you might recall that at the beginning, last time when we were discussing this section, we considered this special sequence that begins with root 2 and extends off in this way. And we asked ourselves, well, what do we know about that sequence? In particular, we want to list some problems that arise in attempting to prove that this sequence converges. So one of the problems, as you recall, is that it's not clear what the limit of this sequence is, if there even is a limit. And that information is important in the definition of convergence, right? Because if you look at the definition of convergence, we like to know what that number A is so that we can compute this difference, AN minus A, and see whether it's small. So if I don't know or have no idea or have no conjecture about what that limit is, then that's a real problem. Another thing that's a problem here, as you might recall, is that there's no really closed form formula for the nth term of the sequence, right? Instead, the best that we can do here, or at least it seems that the best we can do, is to have a recursive formula, right? So here, the first entry of the sequence is root 2. That's our first number that we encounter. And if I want the next entry in the sequence, I can get it from the previous one by taking the root of 2 plus an, like that. So this sequence that we see here involving all of these numbers, this is what's called a recursive sequence. And there we don't have, a closed form expression for the nth term of the sequence. All we know is what it is in terms of the previous term. And again, that's going to give us some problems when it comes time to using this definition of convergence that we learned back in Section 2.2. So in this section, we see that it is possible to overcome the difficulties that we discussed on the previous slide. That is, that it's sometimes possible to know that a sequence converges without knowing its limit explicitly. In order to see how that might happen, we first need to know a little something about increasing and decreasing sequences. So first, a sequence is said to be decreasing if the n plus first term is less than the nth term, always. So this means as you proceed down the sequence, the terms are not getting any larger as you move from term to term. And likewise, a sequence is increasing if the n plus first term is bigger than or equal to the nth term for all n. And that means as you proceed down through the sequence, that the terms are not getting any smaller as you move from term to term. So any sequence that satisfies one of these properties is said to be monotone or monotonic. Now you might remember last time we had this example where we had these 4 sequences and together we determined whether they were monotonic. And the answers, remember, were yes, no, yes, and for the sequence on the previous slide, also yes. Okay, so how did we come to those conclusions? Well, in part A, if you look at the terms of this sequence, remember the natural log function is an increasing function, and so this is a monotonic increasing sequence. Part B, the terms are just bouncing back and forth between -1 and 1, so they're not steadily getting larger or steadily getting smaller or anything like that. They're just bouncing back and forth. Item C, this is going to be a decreasing sequence. Remember that 1 over 2 to the n, that those terms get smaller as n gets larger. And the sequence on the previous slide is increasing. Okay, so the punchline, or the main point of this section, is the monotone convergence theorem. What it tells us is that if you take any bounded monotonic sequence, then that sequence must converge to some limit. So you might recall that the last time we were together, we did actually prove the monotone convergence theorem. This was back on February 6th, I believe. And instead of going through that entire proof again for you, what I do want to remind you of is that the key element in the proof is this completeness axiom. So you might remember the completeness axiom back from chapter 1. Remember, it says that any sequence of real numbers that's bounded above has a least upper bound. Okay, so up to this point, we've merely been reviewing material that we talked about on February 6th. So now we're going to break new ground and discuss an example. In fact, most of the rest of the video is going to be occupied with this example where we're given a sequence, xn, and we're going to use the monotone convergence theorem to prove that it converges. Okay, so one thing that you might notice about this sequence xn is that it's a recursive sequence. And so before we dive into the solution for this example, we might first just amuse ourselves by writing down a few terms of the sequence. So we're told that the first term is 3. x1 is 3. But then to get all of the remaining terms, we need to use the recursive formula. So for instance, if I want to get x2, the next term in the sequence, I need to take 1 over 4 minus x1. But x1 is equal to 3. So that's 1 over 4 minus 3, which is otherwise known as 1. And so I know that x2 is equal to 1. And you could continue and discover that x3 is equal to 1/3. And maybe it would be nice for you to compute a few more terms just to see what happens. So once you do that, you might observe a few things about the sequence. First of all, it looks like all of the terms are strictly between 0. Well, they're bigger than 0 and less than or equal to 3. So all of the terms in absolute value are less than or equal to 3. And so that means that the sequence appears to be bounded. The other thing you notice is that the terms are getting smaller, right? You go from 3 to 1 to 1/3 and down from there. And so the sequence is decreasing. That is, the terms are certainly not getting any larger as we move from term to term. So those are our observations or our conjectures about this sequence. So what we want to do in the course of this example is to verify that intuition we have. We want to prove that the sequence is bounded. We want to prove that the sequence is decreasing. If we can do those two things, then the monotone convergence theorem will tell us that this sequence, xn, must converge to a limit. Okay, so our first order of business is to show that the sequence is bounded. And we're going to do that using the method of induction. Now, many of you, certainly in Math 470, have seen the method of induction in Math 215, and you've probably used it fairly recently. Those of you in Math 570 may not have seen it recently. If so, then I recommend that you go back to Section 1.2 in the book and read about induction. Or you can just go online and watch a little video about how proof by induction works. Okay, so anyway, back to the main story. We're going to show that this sequence is bounded by verifying that every term in the sequence lies between 0 and 3. That is, every term of the sequence is positive and less than or equal to 3. Now, you might recall that induction begins by verifying the base case. So that is, we start at the very first term of the sequence. We ask ourselves, does x1 satisfy this inequality? The answer is yes. x1 is equal to 3. So it is bigger than 0 and less than or equal to 3. So we're good with that inequality. And that satisfies what's known as the base case of our induction argument. So from here, we go on to what's known as the induction step. So now we imagine a world where we have a value of k that's bigger than 1, and we imagine this world where the k minus first term satisfies the desired inequality. What we want to do then is show that that implies that the kth term, x sub k, must satisfy the desired inequality. All right, so what we're going to do is we're going to look at this chain of inequalities here. So we begin with 1/4, and we notice that because x sub k minus 1 is positive, 4 minus x sub k minus 1 is going to be smaller than 4. And therefore, the resulting fractions are bigger, right? When a denominator gets smaller, a fraction gets bigger. So that handles that first inequality. Now, how small can this denominator be? Well, the smallest it can get is when x sub k minus 1 would be equal to 3. Now, when x sub k minus 1 is equal to 3, then the denominator is 1, and you get this fraction 1 over 1. Okay, now, if you look at this expression in the middle here, that ought to look familiar. In fact, that's our formula. That's what we would use in order to obtain x sub k using our recursive formula. So this says that x sub k, whatever it is between 1/4 and 1. And any number that's between 1/4 and 1 is certainly positive and less than or equal to 3. So those two steps, the base case together with the induction step, that completes our proof by induction that the terms of the sequence are positive and less than or equal to 3. So that means that the sequence is bounded. So the next thing for us to do in this example, now that we've shown that the sequence is bounded, is we want to show that the sequence is decreasing. And again, we're going to use proof by induction to verify that it's decreasing. So one thing that you might remember on the previous slide, we had computed a few terms of this sequence, right? It was started with 3 and it went down to 1 and then to 1/3 and so on from there. So the first thing we do in induction is we have this base case. Does it work? Does the desired inequality work at the very beginning? And notice that x2 is indeed less than x1, less than or equal to x1. So now we move on to the induction step. So we suppose k, imagine a world where k is some number bigger than 1, and we imagine the scenario that the kth term is less than or equal to the k minus first term. We want to show, in the event that this is true, that that will imply that the k plus first term is less than or equal to the kth term. So as on the prior slide, we go through a chain of inequalities here. So because xk minus 1 is bigger than or equal to xk, that implies that 4 minus xk minus 1 is less than or equal to 4 minus xk. Now, if we take the reciprocals of these objects, that will flip the inequality. So that will say 1 over 4 minus xk is less than or equal to 1 over 4 minus x sub k minus 1. But remember that these doohickeys here, these are just, recursive formulas for xk plus 1 and xk, respectively. Remember, go back up here and look in the statement of the example what the recursive formula is. Okay, so we have started by imagining a world where xk is less than or equal to xk minus 1, right here. And we've shown that that implies xk plus 1 is less than or equal to xk. So that is the induction step. So once we have done the base case and the induction step, the induction argument is complete, and we can conclude that xn plus 1 is bigger than or equal to xn for all n. Okay, so we now know from these two slides that xn is bounded and it's decreasing. So that means that the monotone convergence theorem applies, and so we know that this xn, it's got to converge to some limit L. Okay, the next thing, and this is really quite remarkable, is, okay, we're again doing the same sequence. We have just shown that it must converge. Now, we don't know its limit a priori, but it turns out we're going to be able to compute its limit. Now that we know that the limit exists, we're going to be able to figure out what it is. All right, so again, thanks to MCT, we know that this sequence converges and that it has a limit L. So now we can take advantage of this recursive formula here. Remember, to get xn plus 1, we take 1 over 4 minus xn. So now what we're going to do is take a limit on both sides. I know that the xn plus 1, that's essentially the same sequence xn, right? And so when we take its limit as n goes to infinity, we should get L. And we've already decided that the xn's go to L. And lo and behold, we now have an equation in L that we can solve for L. And if you go ahead and solve this equation right here for L, you will wind up with L equals this maybe unexpected number. It's 2 minus the square root of 3. So that is the limit of this sequence. Okay, now here in this box, there's a little job for you to do. You might notice that in this equation here, right here, the one that you solved for L, how do you do that? Well, you're going to clear the fraction, multiply both sides by 4 minus L. When you do that, you're going to get a quadratic equation in L that you'll need to use the quadratic formula for. And this question down here in the box asks you, well, in the quadratic formula, you get a pair of solutions. How did we choose one of those pair in order to be our limit? So I would like you to think about that. Okay, so we finished the video here with a quick cautionary example. So here we have a sequence, a recursively defined sequence, yn, where the first term is 1, and subsequent terms are computed using this recursive formula. Now, before we go and compute a few terms of the sequence like we did in the last example, let's jump the gun a little bit and suppose, okay, let's suppose that the limit of this sequence exists and is equal to L, and we're going to compute L using the method that we had in the prior, on the prior slide. So remember that to compute the limit, we use the recursive formula here. And we know that as n gets large, the terms of the sequence yn are getting close to L, at least that's what we're told. And so on the left side, we're getting close to L. On the right side, we're getting close to 3 minus L. And that says that 2L is equal to 3, or that L is equal to 3/2. Okay, now let's go and compute a few terms of the sequence and see what's going on there. So y1 is equal to 1. We're told that. To get y2, I'm going to take 3 minus y1. But that's 3 minus 1, which is equal to 2. So the next term of my sequence is 2. And then y3, I take 3 minus y2, which is 3 minus 2. And that's equal to 1. And now guess what? When I take y4, it's 3 minus y3, and now you know the drill, right? This is 3 minus 1, which is equal to 2. And so this sequence, it's going to bounce back and forth between 1 and 2, always. Right? And so this sequence, this yn sequence, it doesn't have a limit. Okay, so this is why it's important to verify that sequences have limits before we go and use these computational techniques to like compute a limit, because you know you could very well wind up computing something that's nonsensical.